Hello and welcome. Today we're going to introduce the beta function, which is closely related to the gamma function. And when I say closely related, if we have a problem that involves beta functions, almost certainly there'll be some gamma function work associated with it. So first of all, without wasting any time, so before you can actually access this, I have uploaded several videos on the gamma function introduction, build up your techniques and your ideas. So now we can move to the beta function, which is another integral function. So let's write this definition as to what the beta function stands for. So the beta of m comma n is defined as the integral from 0 to 1 x to the power of m 1 minus x to the power of n dx. So two bits in the argument, m and n. I forgot there the minus 1, so that's a terrible start already. N is commutative, so it doesn't really matter which is the m and which one is the n. You can feel free, of course, to. But basically, what I'm saying is the beta of 7, 4, it's exactly the same as the beta of 4, 7. It makes no difference which way the two quantities are appearing. There is now a second result, which later on in the course I will in fact prove. At the moment I'm not going to prove it, but this is the relation between the beta and the gamma. So the beta of m comma n is in fact the gamma of m times the gamma of n divided by the gamma of m plus n. So these are the two important results that we're going to use for today. Pardon me about my cough. My cough is very bad today. And by the way, this is the main definition for the beta, but there are two alternate definitions. One is very important. It's a trigonometric one, which I think on the next lecture I'll go through it because it's very, very important, very, very useful. But there's also a third one which I might use from time to time. And the third item that we really need to know today is all the results from gamma. So beta requires gamma. So if you haven't looked at all the videos on the gamma function, please do, because a lot of these things will not make sense. So let's start. A little bit of practice. Pardon me, I almost choked. So, oops. So we're going to start with an integral. 7x to the power of 5. 1 minus x to the power of 4. Okay. This integral looks very simple. It looks like it can be done with A-level knowledge, but I'm not quite sure if it can be done because substitution, it might be a bit of a problem. We can use a substitution. U is 1 minus x, but then we're going to have a bracket to the power of 5. So we'll make no progress. But this is a beta function. Let's put the 7 on the other side. And let's compare with the main definition. So this is in fact, if we look at this definition, the beta of 6 and 5. Remember, is one more. So in order to get that should be 5 there. So that's a 6 minus 1, so that's a 6. And the same thing for the other one. So how do we evaluate this? We need this result. So that's 7 times the gamma of 6 times the gamma of 5 divided by the gamma of 11. And remember, if we have positive integers of gamma, these are factorials. I'm just reminding you the gamma of n plus 1 is of course n factorial. So for example, gamma of 8 is 7 factorial, 1 less. So for this particular one, I hope you can see, I'm going to take the bigger gamma from the top. So that's a 5 factorial, first of all. Let's write it. 5 factorial times 4 factorial divided by 10 factorial. And if I take the bigger factorial from the top, I can cancel it with part of this 10 factorial as follows. 10 times 9 times 8 times 7 times 6, and then the rest I'm going to write as times 5 factorial, so that's the rest. And of course on the top we still have a 4 factorial, I forgot to write it. So that's the 7, 5 factorial, 4 factorial, and the 10 factorial I wrote it like that, so I can cancel the 5 factorial without evaluating it. And I can cancel the 7 from in there. And now what do I have in there? I have a 24, that's the 4 factorial. And I'm not gonna work this number out, I'll cancel a few bits. So 8 times 6 is 48, and this is a 2 in there because there's 2 lots of 24. Of course you can use a calculator, I mean at the moment I'm not good at calculate, the numbers are not too bad. So I make this in fact 1 over 180. So that is not that difficult if we think about it. Okay, let's look at another example of the beta function. So let's make some space. One more for today, that's more than enough. Next time I will put the trigonometric definition, and we'll be working with some slightly different integrals. So here, integral 0 to 1 x to the 4 square root of 1 minus x squared. We have 2 problems with this particular integral. This at A level, probably we're using the substitution x is sine theta or cos theta or something like that, and with this trigonometric substitution I think this might evaluate, it will take a little bit of time, but it will evaluate with further maths, kind of like knowledge a little bit. But we're going to do it by the beta function. At the moment it's not quite ready. Even if we write this to the half, can this be, of course, half of course can be anything. We still don't have the right thing. The problem is this x squared in there. So I'm going to use a substitution. So I'm going to say x is the square root, the positive square root of sine theta. X squared is, of course, a sine theta. And therefore, what can I do in there? Do I want a substitution like that? No, perhaps no. I'm going to, because I'm getting absent-minded. I thought I'm doing A level here. Okay, I'm going to reduce that x squared into a single variable. So without square. So I'm going to say u is equal to x squared. Sorry, I'm going to be absent-minded there. U is equal to x squared. So du by dx is, of course, 2x. So my dx will be du divided by 2x. And the limits, 0 in x will map back into 0, and 1 will map back into 1. So if we look at what happens in here, first of all, let me leave the x to the 4 as it is, because it will cancel with this 2x at the bottom in there. This will become now the square root of 1 minus u from my substitution, and my dx will be, of course, du divided by 2x. Bit of a tidy, so this now will give me, let's move this half on outside the integral, that's from there, and that's going to give me an x cubed, and I'm going to write this in index notation as 1 minus u to the power of a half, and then we have, of course, the du, and of course we need to switch everything into u, and I need that x cubed now. So if I take u is equal to, oops, if I write it here, x is equal to, u is equal to x squared, and raise both sides to the 3 over 2. Hope we can all see that. We'll get x cubed is equal u to the 3 over 2. So eventually we'll have a half, and that will be u to the 3 over 2, and we have 1 minus u to the power of a half du. So now this is a beta because it has the correct form, but we have this half at the front, of course. We must not forget beta of what? It's one more than what we have in there. So that's 5 over 2 and 3 over 2. and we need to somehow evaluate that. So that using this result will be the gamma of 5 over 2, the gamma of 3 over 2, the whole thing over the sum of that. So that's 2.5 and 1.5, 3, 4. So that's the gamma of 4. So this particular one now, we can perhaps write it as a half. I'm going to leave the two gammas on the top because they're fractional halves of the gamma, which they have something to do with root pi. And I will remind you from the gamma function what we need to do with those. The gamma of 4 is, of course, 3 factorial. So let's get rid of that. So that's 6 there. So that's 1/12 the gamma of 5 over 2 times the gamma of 3 over 2. We won't need this, so I will just get rid of it. And then, so I can just write down and remind you of the recurrence relation from the gamma function, that's why I say all results from gamma. So first of all, the gamma of 3 over 2 is 1 less half of gamma of a half. And the gamma of a half is a well-known result from the gamma function, is the square root of pi. So that is this. Now, the gamma of 5 over 2 is, of course, 1 less 3 over 2 gamma of 3 over 2. But we have already evaluated that here. So that is, in fact, 3 over 2 times a half square root of pi, or 3/4 if you want. So I'm going to plug in my bits. So the gamma of 5 over 2 is times 3/4 root pi, that is this result here, times a half times the square root of pi. And now it's just a bit of a tidy up. The root pi will just give me a pi. Okay, and these numbers now, what will they give me? First of all, 3 goes into itself once, and it goes in there 4 times. 4 times 4 is 16, times 2 is 32. So I'll make this pi over 32. And this particular integral, if you were to try obviously with a sine or a cos substitution, it will be quite involved to get through it. So that's it for today for the beta function. I'll do a few more lectures, try to give you a little bit of basics of this particular thing, which is actually very useful for integration, and it comes, of course, in higher level maths. For the time being, I'm going to be signing out, and I'll see you real soon. Bye for now.